So in the last 25 minutes, I'm going to do a calculation that is not really part of the main course material, but it's just something you should see, and it's the another way of defining geodesics as local extrema. In general, I don't do the calculus of variation stuff, but this one is instructive. And I'm going to do the example of a timelike geodesic in Lorentzian space-time. So remember, Lorentzian just means our signature is -1, 1, 1, 1, so the kind of metric we want for relativity. And timelike means the tangent vector is timelike. It has negative norm. And so the proper time elapsed, the analog of length, is the integral of the square root of minus g mu nu with the tangent vector twice integrated d lambda. So we had this formula in flat space-time where it said eta mu nu. Well, we just send eta to g mu nu, and this promotes it to curved space-time. So this is a useful formula if you're trying to rederive the results of interstellar where they go near a black hole and lots of time elapses, lots of time at infinity elapses, then you need this formula to reproduce the results of that movie and so on. And but here we're going to think of it as helping us define geodesics. So this is a functional from a curve, right? This is a map. So functional is a map from some larger set of points to numbers. So it takes a curve to a number, and the number is the proper time elapsed. All right, so let's try to do this calculation. I always get this wrong, so I'm really going to stare at my notes today. So we need to use the calculus of variations. The claim is that we're going to get the geodesic equation if we locally extremize this functional. And so what we're supposed to do is vary it. So for delta tau, we're going to need to do the variation of what's inside here. So we always assume the endpoints are fixed in this game, so our variation can go through the integral. So we just have this complicated thing. So I'm going to get, first the derivative of the complicated thing. First the derivative of the square root. So 1 over the square root of this thing, dx mu d lambda, dx nu d lambda. And then I'm going to have a bunch of terms where the variation hits all the things inside. So I'm going to have minus delta g mu nu times the same thing, dx mu d lambda, dx nu d lambda. And then I'm going to have 2 more terms, which are going to end up being the same, but let's be explicit about it. So g mu nu d delta x mu d lambda dx nu d lambda minus the same thing again, except for the mu and nu interchanged, dx mu d lambda d delta x nu d lambda, all integrated d lambda. Now, what is this delta g? Well, we can expand that out as well. We want things in terms of delta x. That's the way this game works. So this is the same thing as, by the chain rule, delta x, call it alpha, partial alpha g mu nu, right? This is, we don't even have the covariant derivative in this framework. We're just extremizing this functional. The derivatives that show up are ordinary derivatives. And I guess I'll put the minus so I don't forget it. Okay, now these two terms I claim on the right here are actually the same. So I don't know if this is intuitive to you yet, but basically what you want to do is relabel the indices. So, rename mu to nu and nu to mu, and that'll swap them over here. So the right-hand sides are the same, but now you have g nu mu, but the metric is symmetric, so it's the same as g mu nu. Okay, so this is really a factor of 2 times those terms. And now the trick is, after we've varied, and you have to do this after you vary, or you can get into trouble, we're now going to pick a fun parameter. Now we're going to use, so this equation up here was any parameter lambda. Now we're going to use a specific parameter, and this is where the notation gets a little confusing, lambda equals tau, where tau is now the proper time of the background trajectory. So what, the picture you have to have in mind for calculus of variations, I'll draw them up now since this is time-like, is there's some, background trajectory here. So this is x mu of tau. Not this tau, the tau at the bottom where it's the background trajectory tau. This is the full tau. So you always have this business in calculus of variations where after you vary, anything with a delta becomes a variation, and anything without becomes a background quantity. So there's a background x of tau, and then you're sort of imagining other nearby curves that have something here which is delta x mu. And we regard those as functions of the background tau. So if you haven't done much of this calculus of variations, this might be a bit hard to follow, but feel free to ask questions. Yeah?
How did we say that delta g mu nu is that delta itself?
This thing down here?
Yeah.
Well, that delta is a derivative, so we can just use the chain rule on it. We can have delta act on the coordinates.
Where do we get x from?
G, it depends on x. So everything in this curve is evaluated at x mu of lambda. So g has x dependence, so when we vary it, we do the derivative of g times the variation of what's inside, and what's inside is x. G is a function of x. So we use this parameter, lambda equals tau. And now I'm going to introduce a notation we had in special relativity, and we'll keep using in general relativity, which is that when we're using proper time, the derivative with respect to the proper time is called the forevelocity. And it's denoted u. So dx d lambda is now equal to dx mu d lambda is now going to be called u mu. Maybe 3 equals for a definition. And then u mu has the property that its inner product with itself is -1. So that's something we introduced in special relativity, and we'll use it in general relativity as well. It follows directly from the fact that you use tau as the parameter. And again, you guys did this back in week 1 of the course, so if it looks obscure, you can go study that. So now that I've done that, I can start simplifying this delta tau. So let's have delta tau equals the integral. And see, this factor out front is now totally gone because of this trick. Right? Now that I've used the proper time for my background trajectory, anything in this calculation without a delta on it is now the background trajectory. Now that I've used the proper time, this whole thing in the square root is just 1. So this red equation means this thing is going to 1. Yep.
Does the curve metric also just lower and raise indices without any
Yeah.
additional?
Yeah, if I didn't say that, I should have. The raise and lower indices with the curve metric in exactly the same way.
You don't get any extra factors or anything?
No, just a definition, and it's the only one you could choose because the curve metric, everything we do in curved space has to relate back to flat space in the special case of flat space. So. Okay, so our square root is gone by this trick, and it definitely helps. I mean, you can do it keeping the square root in, but you'll end up with a much more complicated equation, which will end up being the non-affinely parameterized geodesic equation. But this way we'll get a nice one, but it's still a bit of work. So the square root's gone, but we still have all this stuff in here. So the first term with our simplification was minus del alpha g mu nu dx mu d lambda dx nu d lambda. But these things now can be just more simply denoted u mu and u nu. And so this term is now u mu u nu, where u is the background trajectories for velocity. And then from the other two terms, which are the same, we will have 2 g mu nu. Let's write them in the form of the second term.
The delta x alpha in the first term.
Before the d alpha.
I just left it out. Thank you so much. Let's put it at the end. Great. So minus 2 g mu nu. And now we'll have u nu along for the ride, and we'll write the other one as dx d tau u mu. Okay, so now I've commuted the lambda derivative with the variation. And notice that I got a dx nu d lambda, which is a u. And d by d lambda equals d by d tau. So this term here we said was d by d tau, or goes to d by d tau.
That's delta x?
U nu. Delta x, yeah, I told you I'd screw this up. Yeah, it should be d by d tau of delta x. But then I'm missing, no, I'm good. Thank you. Delta x nu. Delta x mu. And this is all integrated d lambda, but that became d tau. Now what do we do with this mess of non-covariant stuff? Yeah, next we're going to integrate by parts. So the second term is going to become 2. This is just an ordinary tau derivative integrated with respect to tau. So that's just going to become plus 2 g mu nu u nu delta x mu. That's the second term, all integrated d tau. So we can discard boundary terms, because that's how you do it in this game. You fix the endpoints of your curve. And the first term is then the same. And then we're going to notice that, of course, this d by d tau could also be written as u mu partial mu, right? Because remember, u mu is dx mu d tau. So u mu partial mu by the chain rule is just d by d tau. Yes?
Why, when you integrate by parts, is it still in the integral?
That's just, sorry, when I say integrate, when physicists say integrate by parts, we just mean use the Leibniz rule. You don't do the boundary. If you're thinking of doing the integral, yeah, use the Leibniz rule and the vanishing of the boundary terms. That's the key point.
In this case, the boundary term indeed vanishes.
Yeah, but by assumption. I mean, it's just part of the way everything is set up. Okay. So let's keep working on this. Let's notice that this last term here can be expanded out as plus 2. We'll have one term where we act on the metric, just dg mu nu, d tau u nu, delta x mu. And then there's going to be another term, g mu nu d2. This u nu is itself dx nu d tau. So we'll have d2 x nu d tau squared. And this will all be times delta x mu. Move this over a bit. And then finally, all integrated d tau. Shouldn't have written the parentheses. Now we're going to have to see everything magically collect together. So we can do one more thing here, which is we can notice that this d by d tau could also be written as a u dot grad type term. So I've now deviated enough from my notes that I'm really going to need your help. So this is u dot partial g mu nu. Now I think it's going to be convenient probably to write everything out. 1/2. So let's see what we've got. Now every term nicely has a delta x factored out, right? So we're going to be able to go way down here and write delta x mu d tau. Now let's get our indices consistent. These were delta x mu's, but our first one we had a delta x alpha. So we're going to have to relabel that alpha. So we're going to call it mu. And then I guess what I'll do is I'll change the mu and a nu to alpha beta. So this is the first term. I've just relabeled some indices. And now I've got some more terms. I've got plus 2 u alpha u nu del alpha g mu nu from that second term if I copied it down right. And then I have from d by d tau being u dot grad or u dot partial. And then finally from the third term I have 2 g mu nu d2 x nu d tau squared. Now we should be able to pull out our factors of u here. So this is going to be true for any curve, right? So because it's true for any curve in this calculus of variations game, we get to conclude that this thing must vanish. So for any variation about the curve, the integral vanishes because the variation is arbitrary. The integrand vanishes. So then I'm just going to write that down, and I'm going to write it as, let's pull this to the other side. So let's write it as 2 g mu nu dx nu d tau squared equals positive del mu g alpha beta u alpha u beta minus 2 del alpha g mu nu u alpha u nu. And now it's starting to look almost like an equation for the curve, which is what we set out to do, right? Get an equation for dx nu d tau. So all I need to do is hit both sides with an inverse metric, g mu, I don't know, gamma on that side, and g mu gamma on this side. And then let's see what happens. So this becomes Kronecker. So this just moves that nu to a gamma. So the left-hand side, and what I'll do is I'll move the 2 over as well. So let's get rid of the 2 and put a 1/2 there. So the left-hand side now just becomes that should have said d2x nu, it becomes d2x gamma d tau squared, and equals 1/2 g mu gamma. And now I think I probably want to do some index relabeling. We should probably change this nu to a beta, because then I'll have u alpha u beta. So I'll have del mu g alpha beta minus 2 del alpha g, and it's now is mu beta. U alpha u beta. It's looking simple, but not quite there. And now the trick is, we notice, and you had to do this on your homework when you did the Maxwell problem I made you redo a while ago. We use our tricks. We notice that this thing, alpha beta, is symmetric under interchanging alpha and beta, which means we get to freely interchange alpha and beta in this parenthesis thing that's multiplying it. So I can write this as G mu gamma. And get ready for the grand finale. It's coming just on time. I can write this as two terms, del alpha G mu beta minus minus del beta G mu alpha U alpha U gamma. What's that, Evan? Anyone recognize this?
It's negative 1 times the Christoffel.
It's the Christoffel symbols. So at long last, I'll hold you 2 extra minutes to be triumphant here. At long last, after this huge mess of derivatives, things finally collapsed into something covariant. Because what do we have? This is exactly minus gamma mu upper lower alpha beta U alpha U beta equaling this thing here. But put them together. Gamma, thank you. I have to be correct when I'm triumphant. Gamma is the upper index, and so we have d2 x gamma d tau squared plus Christoffel gamma alpha beta U alpha U beta equals 0, which is exactly the Christoffel form, if you go back in your notes, of the perfectly covariant equation d by d tau U gamma equals 0. Okay, so after this long mess coordinate calculations, it collapsed down to this beautiful form, which it had to because we knew this was the right math for describing invariant statements. And now you know geodesics are also local extrema of length. Okay, thank you for your patience.